So animation number 1, we have a red field detector that we can drag around and put where we want. And then we have the field shown as colored arrows, right? They're not field lines because they're not continuous. And they're not vectors because they're all the same length. So the arrows show the direction of the field. The color shows the field strength. And so just to show that this is a point charge, I can't manipulate it very well on this screen, but you would take this and put it, say, at 1 unit away. And if you did that, you'll get a certain field strength. And if you put 2 units away, if it's a point charge, you would get 1/4 the field strength, right? So very quickly you can tell whether it's a point charge or not. And I think the problem is pretty straightforward, so this one should be easy for you, I hope. Problem 2 shows field lines. And we know that lines leaving a charge indicate a positive charge, and lines entering a charge indicate a negative charge. And so we can see the lines and the directions of the lines, and you know the rules of field lines tell you that the number of lines are proportional to the magnitude of the charge. And so in this problem, it's a matter of counting lines, and what you want to do is get the charges far enough apart that it's easy enough to count the lines properly. So just follow the instructions. I think this problem should be straightforward as well. Number 3, you just have to match the charge arrangements A through E with the field diagrams 1 through 5. Let's show diagram 3. Okay, and I think this one you should be able to puzzle out. This diagram, for example, doesn't look symmetric around X and Y, so likely it's one of these triangular arrangements, right? And the lines are going in, and so a blue charge, that would be a negative charge, and so it must be either B or C, or could it be D? So anyway, you need to compare all 5 field arrangements and all 5 patterns and see how well you can do. If you get it wrong the first time, you'll be able to try again. And number 4, an electron is shot into a series of field regions, and it does that. In the first region, we see it bending up because it goes in straight, so it definitely bent up. Here, it's not clear whether it's just going straight or it's bending up more, so we'll have to be careful in that region. And here it's moving in this direction, so it's definitely bending down. Here it's bending down more strongly. And just keep in mind that an electron always goes opposite the field, right? The positive charge has a force in the direction of the field. So an electron that bends up means a proton would bend down, and so the field in this region has to be down. Straight down? Well, we'll find out. And if the electron bends down, then the proton would bend up, and the field in this region must be up, and the field in this region must be up, and the field in this region we don't know. So how do we find the magnitude of the field? Do this. We use the definition of electric field and rewrite it so that force on any charge in a field will be the magnitude of the charge times the magnitude of the field. But since it's bending, we can relate that force also equals mass times acceleration. So the force, QE, must be equal to the mass times the acceleration. And we want to find E, so E is simply mq over A, and m is the mass of the electron, q is the charge on the electron. you can look those numbers up and calculate this ratio. It'll come up a lot, and so it's good to just have not just the mass and the charge, but what the ratio of mass to charge for an electron is. And then you got to measure A. So how do you measure A? That's first semester physics. Guess which equation you should use? You should use, as we so often did, equation 3 of the kinematics equations from semester 1. By the way, those equation sheets are on your resource page. And as you'll remember from last semester, in fact, we're learning this right now in Physics 1, this is written as delta x, but in this case, the acceleration is along y, so I write it in y. The initial velocity has an x component, but no y component. So the vy, when it enters here, the vy is 0, but the vy is going to change. But we don't have the information about y. But we can measure with the cursor what the... actually, we do have the information about y. It's given, I take it back, it's given in this table. So in that case, I think later on in the assignment you won't have the velocity. When you don't have the velocity, you want to use this equation. So since you have the y velocities, what are we going to do? We're going to use the equation. You can just use the equation. The acceleration is the change in velocity over time, because we have these velocities. So actually, I notice the x and y positions are given, and the vx and vy's are given. And so you could use either of these methods to get the acceleration, and once you have the acceleration, you can get the field. Just keep in mind the direction. For an electron, the field is always opposite the force. Another problem of a similar type. Okay, so this one's could be a little more complicated, but the idea is the same. You want to find out what the acceleration is in each region. Clearly in the green region, it bends up because it enters horizontally. And then in that reddish salmon region, it's not clear what it's doing, and in region 3, it appears to be bending down, and region 4 bending down more strongly. But once again, you have all this position and velocity data, so you can see if there's no change in the velocity in the x direction, then the force is only in the y direction. And if there's change in the velocity in the x direction but not the y, then it means there's a force in the x direction. So watching for accelerations by changes in velocity in each region is what you want to do. Once again, more of the same. Only this time you don't have the velocity information, but you do have the cursor, which gives you the position information. So remember that equation number 3 is what you want to get the acceleration and get the field. All those same equations that I talked about back in number 4, I think it was. And again, only this time the electron's coming down. And in this case you have all the position and velocity measurements for you. So another problem of the same type. Hopefully by now you're good at it. So you have two fixed charges that you're given their magnitudes, and you have, can I move this? Oh, I can't move it. There we go. If I take this out of the way, you see that the point at the center, the positive charge, is exerting a force up along the diagonal, and the negative charge has field lines going into it. So the force at the center, the electric field, excuse me, at the center is strongly along the axis between the two charges because the field is all in that diagonal going up direction. So think about, I don't want to spoil your fun, think about where you're going to put that red charge so that all the field vectors will cancel and the total electric field, right, which is going to be the sum of three vectors, will cancel. So see if you can think about that and then play around with it. And then once you find the position where the electric field at the black dot is 0, then you can find the unknown charge. And how are you going to do that? That's exactly what you've been doing in the assignment, so you should know how to do it. So by all means, try and do it on your own. But if you're really stuck, I'll give you a hint. So there were three charges. So the field at point P, that center black dot is what I'm calling point P, is the sum of three vectors. And the three vectors are the electric field at this point due to charge A, charge B, and the unknown charge. But you're going to place the unknown charge so that the total electric field at that point is 0. And so now the equation reads 0 equals the sum of these three charges. And since the field due to these two are along the diagonal, let's think of this as our x-axis. It'll just make things easier. These are both positive, and this has to be negative. It has to cancel out the sum of these two. That gives you a hint of where you have to place it. And so we can simplify this equation. Try simplifying that. Don't be lazy. Try and do this on your own. So anyway, I took this and I rewrite it. And remember, where these two vectors are going to be in this direction, even though this is negative. And this vector, the vector due to this, has to be opposite along the diagonal this way in order for it to sum to 0. So I put the absolute value signs, which means you're going to ignore, these are both positive charges, this is negative, but you're just going to put in magnitudes. So notice, the magnitude of the KQ question mark over R question mark squared has to equal the sum of these two vectors. So just remember, we have absolute value signs. So notice there's a k in every term, so we can divide through by k. That's convenient. So you don't have to worry about the k. And the QA and the QB we know. And the R question mark squared you're going to have to measure. And so the Q that you're looking for is just going to be these two terms multiplied by the R question mark squared. Now what are these R's? I hope you know. So the field due to charge A at the center point, that's what we get to 0, is this distance. So you got to get that distance, right? That's the RA, the distance from the charge to the point. Follow that. And RB, of course, is the distance from charge B to the point. And you can see that's going to be the same distance. And then this charge, this unknown charge, you have to place it. And then with your cursor, measure the distance from the point to the very center of the unknown charge. And that'll be your R question mark squared, which you'll multiply both sides of the equation by to get your Q. All set? Good. Number 9, we have 4 point charges of equal strengths but two different polarities. Right now it's set at 0, but we can slide it this way or slide it this way and change the polarity. When I'm this way, you can see that charge 1 and 2, the direction of the field is away from the charge. So charge 2 and 3 have to be positive, and charge 1 and 4 have to be negative because the field is pointing into the charge, and if I slide it the other way, whoops, it's not going, but anyway, if I slide it the other way, then I reverse the polarity and the strength of the field. So let's go the positive side and know that the field at that black dot is going to be the sum of 4 field vectors. So if we go to charge, the field due to charge 1 at this point would be a vector that way, right, because it's a negative charge. And the field due to charge 2 is positive, so it would be down and big. And the field due to charge 3, since it's positive, would be up and big and equal, so those two vectors are going to cancel. And then the field due to 4, it's a negative charge, so it goes from the point toward the charge. And because the distances and the magnitudes of charges are the same, you can see that vector from charge 1 and vector from charge 4 are going to be equal, and their y components are going to cancel, but their x components will add. And so there'll be a net field in this direction, which will be the sum of the two x components of these two vectors. So to get the total field, we just need to get either one of these vectors, 1 or 4, find the x component, and multiply by 2. Let me write that down. Okay, so see what I'm doing. I'm getting the field here, realizing that charges 2 and 3 cancel, and the y components cancel. So the only thing that ends up contributing to the field at point P, when I add all those vectors together, are the two x components of, oh, that should be 4, e1x and e4x, and they're in the negative I hat direction for this arrangement. And so I could rewrite it as that the total field is 2, because these are equal, times either one. So I'm taking the e1x, putting the negative there, and it's in the I hat direction. So now we got to get, how are we going to get e1x? Go ahead, write it down before I show you. Do it yourself. So we just use the point charge equation. E1x is going to be E1 k q1 over r1 squared to get the x component times the cosine of theta. So the q1 is the charge, the k is the k. The r1 is this distance, right? Always remind yourself the distance in that equation is from the charge to the point, or the point to the charge. And the angle to get the, has to be this angle here. So let's see how we're going to get all that. I should say, how are you going to get that? So go ahead and get it, and then come back and see what I did and see if we did the same thing. Actually, I'm not going to do it out for you. So this distance is a right triangle. This is s. This is s over 2. What's this going to be? It's got to be bigger than s. So it's going to be s squared plus s over 2 squared, or s squared over 4. So s plus s squared over 4. That's 5/4 s squared, and then you take the square root. So this distance is the square root of 5 over 2 times s. But it's going to go in here as the square, so that's going to be 5/4 s squared, this distance. And then this angle here, between this hypotenuse and this line, is this angle here. And so the cosine of this angle, picture it, is the adjacent s over the hypotenuse. So see if you can figure out what's the... So the cosine of that angle, which is this angle, is the adjacent, 1s, s or 1s, over the hypotenuse. square root of 5 over 2s, and so the s cancels, and the cosine of the angle is 1 over the square root of 5 over 2, or 2 over the square root of 5. You don't actually have to find the angle, because all you need is the cosine of the angle. But there are other ways of doing it. That, I think, is the most direct way. And then you go down here, and actually up here, and you do your k, q1, r1 squared times the cosine of the angle, and then you multiply that by 2, and it's in the negative I hat direction. Gee, I did the problem for you. Okay. Okay, in this problem we encounter a line of charge or a charged rod, and we see it from two configurations. One where the point is along the line or axis of the rod, and the other where the point moves perpendicular to the rod or along a normal or perpendicular bisector of the rod. So before we do this, the instructions in the lab talk about something in class which we haven't had. Let me spend a few minutes talking to you about point charges, charged rods, and charged plates. These are something that you should be familiar with. So I'm going to just digress for a second, and give you a little discussion of that. Okay, you know what a positive charge looks like, and these are field lines that are going out, and I'm just not drawing them all the way, but they keep going, and they spread out like rays of light from a light bulb, and we know that this has a 1 over r squared dependence. Now when we get to the charged rod, notice that at the ends the field lines are spreading out, sort of looking like a point charge, but in the middle they're uniform, and if field lines don't spread out, it means the field isn't getting weaker. So it appears that if you go along the axis of the rod, the field isn't getting weaker. But if you take this rod and you rotate it perpendicular to the page 90 degrees, so you're looking down the axis of the rod, it's going to look like this. So along this angle of sight, the charged rod looks like a point charge. Along this plane of sight, it looks like a uniform field. And so the result of that, if you understand the logic, is that this has a dependence of 1 over r. It does get weaker because the rod is doing this along one axis, but it's uniform along the other axis, so it gets weaker as 1 over r, as opposed to the plates. When we get to the plates, I haven't drawn all the lines, but if you imagine a big plate of charge, the lines are all going up, and the only place they diverge, and going down too, are at the edges of the plate. And so the way we create a uniform electric field, which you saw in the earlier problems, is to take two charged plates. So if you take an upper plate, which is negative, this is a little hard to picture, and a lower plate, which is positive, the field lines are going to all go uniformly from the lower plate to the upper plate and only kind of bend around at the edges. So when we, in those earlier problems, was firing an electron through a uniform electric field, the way you do that in the real world is to fire an electron between uniformly and oppositely charged electric plates. And so this has no R dependence. If you go inside the plates, the positive and negative plates, everywhere the field lines are uniform. And so the electric field strength is uniform or the same everywhere inside the plates. And so the force on a charge passing through those plates, since the field is uniform, the force will be uniform. It won't be zero, but it'll be uniform. And that's why you got a constant acceleration, because the force, as an electron moves through here, it's experiencing a constant force, but a constant force, not a force that's changing. So those three arrangements are important, and in this problem you're seeing a charged rod. So remember, a charged rod, if you're close to the rod, is going to have approximately a 1 over r dependence. But if you look at this rod and you walk 100 meters away, the rod is now going to look like a point charge. So it's only when you're close to the rod and the rod is more or less like an infinitely long rod, or approximately like an infinitely long rod. And the same way with the plates. The plates have to be big, because if you have two plates and you're near the edge, the field isn't going to be uniform. So you have to have two plates close together that are fairly large to get this uniform electric field. Okay, this is going to come up again in future assignments and labs, so it's worth knowing. Okay, let me just show you a few images that I got from the web about uniform charge rod. So this is kind of helps you visualize. We're looking along the rod, and you can sort of imagine if I rotate it, it's going to look like a point charge. Give some sense of the three-dimensionality of it. This doesn't have the three-dimensionality, but it just shows you that if you're close to the rod, the field appears to be fairly uniform. Notice this is a negatively charged rod, so the lines are going in. And as long as you're fairly close to the rod and not near the edge, it has a uniform nature in this plane. But if you're able to rotate it 90 degrees out of the plane, it would look like a point charge, and that explains the 1 over r instead of the 1 over r squared dependence. And this one, I don't know if that's helpful, but it gives you some sense of the three-dimensionality of what the field would look like. And you can see that this rod, the lines are spreading out. If you get far enough away from this rod, it's just going to look like a point. But if you're close to the rod, like right in here, then the field lines in this direction aren't spreading out. And it's only when you rotate the rod and look down the axis that you see them spreading out. So once again, the 1 over r dependence. And then we can go to the charged plates. Whoops. So you don't really see the three-dimensionality, but it does show you that between the two plates, the field lines don't spread out, and so it's uniform. And you just have to imagine that these are two plates, not two rods. It's only near the edges where the field is not uniform. And here's another one. Again, it doesn't show the three-dimensionality, but it shows that between the plates, the field is uniform, but outside the plates, it starts to look more like a dipole, actually. And here's an example. This is actually how we do it. We take a battery and we take two plates. If we were in lab, we could do this. And the plates charge oppositely according to the battery, one positive and one negative, and between the two plates you get a uniform field that does not vary with position, right? That's the key to this type of field, is that you move around between. It's only when you get to the edge of the plates that the field starts to get weaker. Okay, So you have the two arrangements, and the exercise walks you through what you need to do for the two different arrangements, placing the thing in certain positions and collecting data and doing some calculations. And so close to the rod, you should see close to approximately that 1 over r dependence. And the further away you get from the rod, the more the dependence starts to look like 1 over r squared, because the rod itself, far away from the rod, it will look like a point charge, whether you're along this direction or this direction.